Hello everyone, welcome to Final Element Method tutorial. Today we're going to use Abaqus to do an aircraft fuselage analysis. So here's the problem statement. Assuming you have this one segment of fuselage and you have a window in the middle. The size of the segment is, the length is 15 inches. The radius of that is 100 inches. The thickness, we're going to compare two different thickness. One is 0.08 inches in thickness. The other is 0.04 inches. So it's like 2 times thicker than the other. And the window size, you have your horizontal width of the window is about 10 inches. The height of the window is about 15 inches. And the distance from the center line to the window is about 30 inches. And the radius of that, we have a fillet for the window, and the radius of the fillet is 2 inches. As for the load, first of all, since in the air cabin, you have larger inner pressure than the outer pressure. So we're assuming it has a single pressure of 9 psi. And record with a single pressure for a closed-end cylinder, you should have a longitudinal stress of PR over 2T, which for our case is about 56 to 25 psi, and for the thick plate, and about 11,000 for the thin plate. And you will have a hoop stress, which is sigma, and it should be equal to PR over T, and it's 2 times larger than the longitudinal stress. However, since we are only simulating one segment of that, it's not a closed end, but in reality, it is a closed-end cylinder, so we need to manually apply the longitudinal stress to the side. In Abaqus, we are going to use shell element, which will apply the longitudinal edge loading for that, and the unit for that is Newton per meter, or psi times inches. So you have to use your longitudinal stress multiplied by the thickness to obtain the value for that, which is 450. And here is a 2D graph for the applying boundary condition and load. For this surface, as this surface is perpendicular to your x-axis, so we should apply the x symmetry to this surface, like this. And for this end, since this surface is perpendicular to z-axis, we're going to apply the z-symmetry on this end. And the bottom surface, since in the real case, we cannot have deformed, like the bottom surface cannot have moved to the right or to the bottom. So we apply the YZ direction pin to this edge, but we allow this one to expand. That means it has a x direction displacement. Finally, on this end, on the left end, we should apply the shell edge loading with 450 as the amplitude. So one main concern in this problem is we want to see whether the stress is over the yielding stress going to the uh, going to the plasticity region, or it still remains in the elastic region. So what we are going to use is a real material property of 2024 T3 aluminum alloy. And recall that we later will find the real material property from the tensile test handbook. So recall that all your tensile tests is recording the engineering stress and engineering strain, which has the definition of the load over initial cross-section area, or the changing length over the original length. Or you can write as an integration of the changing length divided by the original length. But in reality, what is acting, as this curve shows, what is acting on your specimen because of the necking effect, you should have a smaller applied area than your original area, which means the true stress inside your specimen should be way larger than the original one. So with the assumption that the volume is incompressible, so there's no volume change in the solid, you would have your true stress equals to load over the actual area, which is this one. And your true strain is integration of, for each moment, you will have a change in length over length, and do integration, you will get your true strain. And so your true stress and true strain have a relationship inside, and it can be calculated by the formula. However, Abaqus provides you with a tool that can convert engineering stress to true stress, and we'll show it later in the Abaqus GUI setting tutorial. So the process we've trying to find the material property is following. First, we find the material property from handbook. Normally, we'll find it in MMPDS, the latest version for the MMPDS, which is a metallic material property development standardization. So from the handbook, you can get the tensile test for different temperature, different specimen, and different loading conditions. And then from the curve, we're going to use a tool called image digitization to interpolate the curve into a data. And there's a free software for this step. And we're going to show you how to find the material property. And later, we need to import the data we get from previous step to Abaqus, and then use the tool in Abaqus to transform that into a true stress strain curve. And this true stress strain is what we are going to apply in the real analysis. Because for final element, you have to input true stress and strain. And start with finding material property. This is a handbook I have. And we are going to find the material property of aluminum 2024 T3. So we can go to aluminum and open the 2000 series 2024 alloy. And we can go directly to the curve that we want, which is similar to here, but this one is only within the elastic region. So we wanted to go to the plastic region, so we should go even further to that. If it is like the full range, it should include the full range here. So now if it doesn't include the full range, that means it's not the, it doesn't contain the plastic region. So this curve is a full range and it's an aluminum alloy sheet in the room temperature. Three things is very important: the material property, full range, and the temperature. We choose the room temperature. And also you can see other things. For example, this is a rod, but we prefer a sheet in our case. And you can see there's two types of tensile test. One is longitudinal tensile test. The other is long transverse tensile test. Longitudinal tensile test is good for tension, and long transverse tensile test is designed for hoop stress analysis. So we are going to follow the long transverse stress strain curve. And to do the second step, first we need to take a snipping tool to this picture. We need to increase it as large as possible to get enough resolution for the picture. Then we use the snipping tools that the computer has automatically and take these pictures, including the legends. So we can save it as a data. I already saved the picture, so I won't save it again. It's better to save as PNG format because it's higher resolution. And then we can go to the network. I already copy and paste the website I already attached in the PowerPoint. So this is the website that provides you with the image digitization. So load your image and choose the 2D XY plot. And first of all, you need to select 2 points. You can see the zoom in plot on your right corner. And we are going to select this point and this point. This step is to give you a reference of how to calibrate your pixels into real data. And then we need a Y. So again, we choose the origin and then choose the very top one. So when you finish, hit the complete, and your x 0.1 is origin, so it's 0 with x coordinate, and x2 should be 0.2 here. The unit is very important. It's 0.2 inches per inches. And for y, the first point is 0 in y coordinate. The second point is 90 KSI. That means 90,000. When you're done that, here click the add point, and then now you can trace the point. Always look at the zooming plot on your right corner, so you will get a better look at where you are now. So this is your first point, because the first part is pretty linear, so we don't need to do that careful. We just do pretty coarse. Probably select like a 5 or 6 point to that. It will be enough. Like we click a point here, we click a point here, and we click a point here. Now it's the plastic region. So plastic region, it's better to make it finer, so the increment, you can make it not that, you can make the increment like smaller for the region that the curve changes slope a lot. And if you want to delete that, you can choose the delete point here and then just click the point you created. And then keep doing that until it reaches the end point, which is this one. Okay, I won't do it anymore. Once you finish this step, once you give enough sampling point, select this view data. And then you can see your data here, and then you can download as a CSV file. And now you can choose that as CSV file, and then just save it to the file folder you want. And I already have the data here in my folder. So, sorry. I already have the data here in my folder, which is a CSV file. So I won't do it again. Now let's go to see Abaqus GUI settings. So first of all, we create a part. Let's call it like a thing wall. So we're going to use the shell element for that, because the thickness ratio here is 100, like way more than 1/10. So we can use a shell element for that. If your thickness to radius ratio is smaller, is larger than 1/10, then probably you need a 3D element for that. Say thin wall fuselage. And we use extrusion here, 200. And we use this to draw an arc. We only need 1/4 of the circle, so we draw an arc here. And it selects 3 points versus the central point, which we make it 0, 0. And the start point is it's drawing a circle clockwise, so we choose the top one, so it's 100. This is a start point, which is the top of your fuselage. And then we choose 1/4 of that is like 100, 0. Now you have your shell. Sorry, did I choose the wrong? I think I choose the wrong thing. Yeah, I choose the solid. You should choose the shell and extrusion and do the same thing. 0, 0, 0, 100, 100, 0. So now you have your sketch. And then when you extrude, our length is 50 inches. Now you should have your part of your shell. The next step is to create a hole on your shell. To do that, we first create a datum plane, and this is going to be your YZ plane, and offset. YZ plane is right located at here, so we want the offset to be larger than the radius. So let's put your radius is 100. Let's put 102. Now you can see your data planes is here. And you select this, create a cut from extrusion, then use your data plane, change that to left view, and then select this edge. Now you will see your right view of your shell. Before we actually create the things, we can create some central line, reference line first. So we do 0, 0. Create a point here, and then probably we can directly draw the line from the 0, 0 here. This is going to be your symmetric line or center line. The other one is we can draw this line to represent the bottom of your shell. Now we can draw the rectangle. You can draw it just randomly here first. Now we use a dimension tool. First, we need this dimension. And this dimension is going to be C, which is 30 here. And then we need this dimension, which is B, and is 15. And notice that this is just a projection. So if you want this arc to be exactly 15, then this must be smaller than 15. So, but now we can just approximate it. It doesn't need to be very accurate. Now we need the length between these two should be the half of A, where your A is 10, so it should be 5. And also this half, it should be 5. Once you're done, just click done, and then we can cut through the entire plate. And then you get your window here. Oh, sorry, I forgot one thing. If you want to change that, you can go to a part, thin wall fuselage, and then in your features, the cut extrusion, change the sketch here. The thing I forgot is I need to have those fillet. Otherwise, you will have the stress concentration at the corner. So we create this fillet with 2 inches as a radius. 1, 2, 3, and 4. Once you change, it has a yellow mark here. You need to regenerate your feature. Now you can see the fillet here. And we're going to copy it and copy another one. We call it thick wall, because your thick wall fuselage is exactly the same geometry as your thin wall. The only difference is the thickness, and we can change it later. And now you have your thick wall and thin wall. We can do the simulation at the same time for thick wall and thin wall. Now we go to property. In your calibration here, we create a calibration. We call it 2024 T6 aluminum. Sorry, it cannot be start with the number. So we call it aluminum 2024 T6. And open your aluminum, this one, you should have data sets and behavior. Let's import the data sets first. Let's call it engineering. So import data sets and choose from the, we can choose all file here, not txt, and then just select the file you just create. Make sure that this is string and this is stress, and click OK. So you can see the points you just selected. And one thing you need to add it here is it's better to make your first value as 0, 0. Since normally it's hard to get 0, 0 in your image digitization. Now what you can do is right click this engineer, do process, convert, and then select the true form for that, and then give him a name, call it just true. And if you compare the true and engineer, this is your true. The ultimate stress can go to 70, 78 or something, while your engineer maximum is only like a 63 or something. So your true stress plus the ultimate stress is way larger than your engineering stress. And finally, in your behavior, you can create aluminum 2024 T6. This is creating your material property. We just use the simplest elastic plastic isotropic model for that. Data set, we use the true engineering. That is very important. Ultimate stress you can calculate it can calculate for you. If it doesn't work, you can select the ultimate stress you have. And the yielding point, we can manually select the linear region for that. And the Young's modulus will be calculated from that. Poisson's ratio for the aluminum, you can get it from the handbook, but we can also just enter 0.33 for that. Finally, we create this material called aluminum 2024. Sorry, it's T3, it's not T6. And then we hit, by the way, we need to change this one. I forgot to change this one. This is doing like doing sampling point between in your plastic region. You can make it a little bit finer if your curve is not, plastic region is not that linear. Now we can click OK. It should say successfully mapped. And let me just change the name to T3. Now you should have your material property here. If you see it, it should include the elastic region where Young's modulus is what we calculated and Poisson's ratio is what we entered, and the table for your plastic region. Create section. Definitely we have two sections. First is, let's go back to the part. First is thin wall. Thin wall, choose the shell element homogeneous, and then for thin wall we have 0.04 inches for the thickness, and we use 5 here. Simpson integration. Material property is what we selected, and okay. And then we need to create another thick wall. Again, the value is 0.08. And since this is thicker, we can increase the thickness of integration point to like 9 or 11. But this must be an odd number. And again, just click OK. Now we should assign the section. We don't need to create set, but let's assign thin wall first. Here, select the thin wall and assign section for the thin wall and choose the thin wall here. Your thickness must come from the section. This is very important step. And the shell offset, we just select MIP surface. Okay, now change to thick wall, assign section, and this must be thick. Once it's done, we can create an instant now. Create two instant. I prefer to use independent to create instant. Now you should have two instance here in the assembly. And however, they are overlapped with each other. To show them more clearly, actually we can remove the thick wall a little bit, like do this transverse rotation and select the thick wall. And we just move it along z-axis for enter a number for that. Let's do 80 here. So click OK. Now check your thin wall. Oh, sorry, I moved the thin wall, and your thick wall is in the original location. Now we need to think about mesh. When you start meshing, because of the hole, you cannot get a perfect mesh. Especially far field, you want it to be kind of square. So we need to create partition for this two length. To create partition, again, we can create a datum plane, which is XZ plane. We'll do horizontal partition. That's why we create XZ plane. And remember the height for the lowest end is 30 30 inches. So we do 25 here. Make sure this plane doesn't cut through your hole. And then create another XZ plane. The highest one is 15 plus 30 is 45. So we can do 50 here. Now we can do partition and long click, choose partition using data plane, and then choose this two. And then hit down, select this one, enter. You see it make the partition between your assembly. Same thing for this two, down, select the upper data plane. Sorry, I select the wrong thing. This data plane, create partition. Now you should have three parts. Top part and the bottom part can be meshed perfectly, while the middle part is, you need to use the free mesh for that. Once it's done, we can go to step. The step part is easy. Static and static general. And here, remember to click the nonlinear geometry because we are going to go to the plastic region. And the initial one, you can make it relatively small, 1e minus 4. And this is not representing the time. This is more like representing how much step you need before the solution reaches convergence. So everything looks good. Now check your field output. In your field output, one important things here is in your string, you should have the plastic strain and plastic strain magnitude. Those two are the one that you can check whether your design reaches the plastic region of your stress strain relation. So finally apply the load. First, we need to apply symmetry. X symmetry at the top surface. The step, you should choose the initial symmetry. Let's say X sim. And select the region, which is the top of both structure. And you can see here whether hold shift so you can select both of them. And now apply X symmetry. And then next one is on the right hand side is Z symmetry for both structure. So create Z symmetry. The right edge of both structure. and apply Z symmetry. Now for the bottom, it should be a YZ pin. Call it YZ pin. This one we can achieve by displacement control. So this one and this one. So YZ means U2 and U3 is fixed. And finally, on the left-hand side, you should have a load which is equal to 450. That's already the loading part. So boundary condition we already setting, finished setting. So we apply load here. This is longitudinal edge loading. Now we should choose the step, and then it should be a shell edge loading, and hold shift to select all the edge you want to apply load. And apply traction normal magnitude 450 is 450 here. This one we choose the undeformed area. But see, if you enter 450, it will give you compression. So that means you need minus 450 to actually get a tension. Always remember your longitudinal stress is always a tension. Then finally you need the inner pressure, which is 9 psi. So we apply inner pressure, create pressure inner pressure. Select the region. Because this is a shell element, you need to select the inner surface instead of the outer surface. So we select the brown. And then 9 here. This is pressure. You can see your angle is pointing inward. So everything looks good now. In your mesh, you can see originally it's all in pink, which means free mesh. First, we choose the hold shift and choose the region that we want to change the mesh control, and then select structure for that and turn it into green. Now we can assign a global mesh. Assign a global mesh. The outer global mesh doesn't need to be too fine. 5 inches is so it may be too coarse. Let's do 4 inches. And you can see here, this is too coarse for the hole. So what we are going to do is we assign for all the lines here, you need to make sure that all these lines are selected. So we assign approximate size. Right now it's 3 inch, while we want it to be 0.3 inch. So it should be super fine here. Now we can make the mesh. After meshing, you can see outside is kind of coarse, while near the hole is very fine. So mesh is okay. One other thing is, finally, when we assign the element type, we delete the reduced integration. So your element should be S4 element instead of S4R. Now create your job, call it just like pressure analysis. And I can use my since I have 12 logical processors, so I can actually include like 10 here and apply GPU computing. That will make your calculation faster. And if everything looks good, then you can submit. Open your monitor to see what's the how your data is going. Always look at the warning. The warning is normally don't affect your solution, but it may give you something not reasonable. For example, this one, the first one say, it says time increment request less than the minimum specification. That means your time is 2 cores here. This warning say 2 unconnected region in the model. That's okay. That because we are doing actually 2 analysis at the same time. So we go back to step and we can make this one even smaller, like 1e minus 6. And then go back and run your model again. Again, we see this warning, but it doesn't matter. Now you see that the first attempt and second attempt has error. That means if you see this, it's like the initial attempt is too large, and then it keep decreasing. Oh, sorry, it's kind of hard to see here. Let's wait until it complete. Okay, it's complete. So what the program did is it start from 1e minus 4, which is what we designed it to start with. And but it find out that this is not convergent, so it go to a lower increment and then keep going until it kind of convergence, which is attempt 3, and it works. So you record this and then following that one and then start like doing analysis until it reaches the maximum, which is 1. So when it's done, we can find the result now. This one, if you don't remember which is thin, which is thick, it's very easy to see. This one definitely has lower stress than this one. Then the higher stress definitely must be the thin wall. Recall the formula here. Thin wall always has larger stress than the thick wall. So this is thin, this is thick. And one thing we want to check is S11. This is in-plane stress. So we can check the far field stress, whether it's equal to what we calculated here or not. We choose the node probe value, and then here we select node. First see the thin wall, and then see a thick wall here. With this direction should be the hoop stress. The thin wall is 22,000, while the thick wall is 11,000. It's exactly the same, a little bit offset, but very close to what we have. If you make the mesh thinner, it may be better. As long as the far field looks good, that means this mesh is not very bad. Now change it to S2. S2 means horizontally, which means following z-axis. Now we are going to check this point and this point. So this is your longitudinal stress. For thin wall is 11, and for thick wall is 5600. 5611,000. So longitudinal stress is also okay. That means our mesh doesn't have a big problem. Now we can see the stress distribution. Definitely both of them has stress concentration effect, but because your thin wall is has higher stress, definitely it will have larger possibility to go to the plastic region. To check whether you have the plastic region, choose the plastic strain magnitude. You can see for thick wall, it doesn't have anything. That means you didn't go to plastic region for your thick wall design. While for a thin wall, at the corner, you are in the plastic region. And the plastic exchange is not very small. So therefore, you can see the thick wall is very good, very safe compared to a thin wall. But on the other hand, thick wall is twice double the weight of the thin wall. So in real aircraft design, the density or the weight of your structure compared to the safety of your structure, you need to make a balance of that. And that's all about the aircraft fuselage analysis. Hope that you can learn something, and thank you for watching this video. Hello everyone, welcome to part 2 of the fuselage design. In this part, we are going to compare the different boundary conditions. What does those boundary conditions affect the design? And the cases we're going to compare with is the one we mentioned before with pin in YZ direction and Y symmetric. So Y symmetric means pin in Y direction and also prevent the rotation of Z direction. So let's go back to Abaqus GUI setting to see how do we change the model. This is the result we just have. This is for the thick plate. This is for the thin plate. So what we need to do is quite simple. We just go to the property part here, and if you directly assign a property, for example, we choose the thick one. The reason we are going to change the thickness is to make it more comparable, to make it a fair comparison between different boundary conditions. So we make it all as a thin plate shell. So for example, if you directly select the thick plate and assign the condition to it and choose the thin plate shell for that, it will show you yellow, which means it's overdefined. And here, go to thick plates, section assignments, you will see you have 2 sections here. So we delete the thick one. Now it becomes green. That means it should work good. Check again, like your 2 model, all is about thin wall shell. So you're good. Now let's apply the loading. Previously, we applied YZ pin for both of the structure. Now we change the YZ pin here. Select the region. Now we only select the right hand side region. And for the left hand side, we create another Y symmetry boundary condition. So select this one. and select the Y symmetry. You can see that Y symmetry is fixing U2, but also UR3, which means it cannot freely rotate along this axis. Now everything should be good. We can click the OK here. After some submission of your job, we wait a while for Abaqus to do analysis. Again, it shows us the warning, but this doesn't matter. This one is just saying we're doing two different models at the same time. Okay, 39 step is finished. We can see the result now. Now you can see that both of them are pretty similar. It doesn't affect that much of your, the boundary condition doesn't affect that much of your stress. But if you do a probe value, and we select the node and select the same node here and here, you can see their stress is a little bit different. That is due to your boundary condition different. So now we can compare the stresses and go back to your material property to check the strain. The one that related to your plastic stress and strain is the von Mises stress and the plastic strain. So for this case, the maximum is at the corner, which the maximum von Mises stress is about 50 kilo kpsi. So about the plastic strain, you can see the plastic strain maximum is also at the corner, which is about 1.3%. So let's go back to the property. This one directly give you the plastic table. So 51, about 51 KSI, you should obtain something like a 0.1, between 0.127 and 0.167. So that would be your, this is your true stress strain. So that means the analysis is following your true stress strain relationship. And that's it about our part 2 of the video, comparing different boundary conditions. Hope that you can learn something from this video, and thanks for watching this video.